Alright, everybody, we're back again. So in this session, we're going to talk about the AR1 models, how to construct a autocorrelation function for AR1 model. So we have seen that MA1 we have one cutoff after Q legs. So if you have a MA1, let's say MA1, so you expect to see one spike, leg one. There's one significant spike. So if you're talking about using the ACF again, so this is autocorrelation function to identify for AR models, okay, AR models. So you're expecting to see the tails off gradually. This means if you have an ACF in this form with several legs, let's say 1, 2, 3, 4, 5. So this is the legs. This is the ACF, right? Okay. Then you're expecting to see the ACF actually reduce gradually or converge to a constant. Okay? Most probably the correlation will become, or the serial correlation with further legs will actually getting smaller and smaller, okay, in an exponential form actually. Okay? AR, no matter AR 1, 2, 3, 4, 5, you're supposed to see, theoretically you should see the ACF will reduce or decay gradually to 0. Okay? So now analytically we like to find out whether this is true or not for AR1. Okay? So before we go to MA2 and AR, the higher order of AR models, so let's look at the AR1 models. Okay? AR1. So you know that AR1 we suppose you have XT, then you have a leg of XT itself, T minus 1, so leg 1, okay, plus the ZT. So as we know, the ZT we're following a white noise normally distributed with mean 0, constant variance sigma squared. Okay, so in order to get the covariance, okay, so we start with covariance. So at the leg of 0, okay, so means you have a gamma x of 0. So this is basically the covariance between the xt and xt, where these two series has no legs. Okay, so the leg will be 0. So this will be xt. So if this is the case, then when we expand it, covariance of phi of xt minus 1. So this part also we can have phi xt minus 1 plus z. Okay. So in this case, we have several pairs of value, sigma squared, covariance of xt minus 1 and xt minus 1 plus phi and zt, covariance of xt minus 1 and zt. So the third term, zt and phi, plus phi covariance of zt and xt minus 1. So this basically is the same as this. So you have two terms for that. So last one, you have a covariance of zt squared. Okay? zt and zt basically. Okay, zt and zt. So we, from the other video, we already know that the covariance between the xs and zt will be equivalent to 0 if the s is lag behind the t. Right? So in this case, is obviously you can find out that this is xt minus 1 and zt. So the s here basically is t minus 1. It's lag behind the t. So this covariance will be 0. So this one also the same thing, xt minus 1 and zt. Okay. So the remaining items, two of them, will be equivalent to. So since there's no legs, then the covariance will become the variance so-called, or you have a covariance with leg 0. Okay, which is similar to the left hand side. So the covariance of zt squared, which is a variance. So the variance of zt is supposed to be a constant sigma squared. Okay, so this is sigma squared. So in this case, if I move this to the other side, my covariance of x. So here we have two covariance or variance involved. This is zt variance. If leg 0, then its covariance become variance. Okay? So this will be 1 minus phi squared sigma squared. So in other words, the variance of x series, or the xt here, the variance of xt is equivalent to sigma squared over 1 minus phi squared. So the coefficient phi is going to determine what is your variance of xt. Okay, this series, the AR1 model. So what happens if we're talking about the leg is 0? Okay, so what happens if you're talking about the leg which is larger than 0? Okay, this is what we would like to see. So if this is the case, then we have a gamma x of tau, leg of tau, non-zero. So this will be the covariance of x tau, sorry. xt and xt minus tau. Okay, so the leg is tau here, t minus t minus tau will be. So covariance is an even function. So basically the gamma tau and gamma minus tau should be the same. Okay, so then we do the same thing, expand the value xt phi xt minus 1 plus zt, comma. So this one we just remain it t minus tau. So you have a phi, the linear property, covariance of xt minus 1, xt minus tau. Okay, then plus the covariance of zt and xt minus tau. Okay. So again, this is the same property, xs and zt, when this legs is actually behind the t, so we can just assume that this one is 0. So the remaining item is this, remaining items. So from here we can further extend this to phi. So when you look at this, what is the legs between xt minus 1 and xt minus tau? So this basically will give us the covariance, okay, with the leg. So t minus 1 minus t minus tau. So this is actually tau minus 1. Okay? Tau minus 1. So from this relationship, you can see a recursive relationship between phi x tau is actually related to its previous covariance in the form of leg of 1. Okay, so in this case, you can further expand this value. Phi gamma is phi of rho x. So this one is actually, if this is tau minus 1, then this is tau minus 2. Okay, tau minus 2. Then you're going to have the phi of square gamma x tau minus 2. So now you can further expand this to phi of gamma x tau minus 3, isn't it? So then you have phi power 3, then gamma x tau minus 3. So expand the gamma tau minus 3 again, you will eventually end up to have the phi. So if the number behind it, this end up to, so you see minus 3 power 3, minus 4 power 4. So if tau minus tau, then you have gamma x 0. So tau minus tau, this will be power of tau. So this will be the, not the last term, but it's a function. When the leg is smaller than 0, the gamma with a leg of tau is actually phi power of tau, and then multiply the variance of x series. Okay, so in this way we can construct the covariance function. Okay, covariance function. Now, so for 0, you have a 1 minus gamma square, isn't it? So this one when tau is equal to 0. So if non-zero, tau larger than 0, then you have phi power of tau, then sigma squared 1 minus phi squared larger than 0. Okay, larger than 0. So in order to get the correlation of the ACF, which is the rho of x with a lag of tau, so this term basically is equal to the rho of x tau over the rho of x 0. Okay? So first term basically is variance over variance. So this must be 1, isn't it? For tau equal to 0. Okay, this must be 1. So for tau larger than 0, so this whole term divided by the uh, variance, then you have a phi of, so this is larger than 0. Okay, so in this way, this will be the, or this tau will be 1, 2, 3, 4, 5 until infinite terms. Okay, infinite terms. So what can you tell? What can we tell from this? Let's say, for example, let's say I have ACF, a series with this ACF, and then this is the legs. One, sorry, one. So the 0 is always 1. So the first term actually is looking for the variance. Okay? 2, 3, 4, 5. Okay? Actually, there are more terms involved. So then let's say let's say the phi of your equation is 0.9. So if you look back to the AR1 models, let's say this phi is 0.9. That means 90% of yesterday, let's say yesterday index. If X representing the price index, that means 90% of the yesterday index is going to influence the current one. Of course, plus the unknown noise involved. Okay? So if this is 0.9, then what we are expecting to get is 0.9 power of 1, isn't it? Okay, so you should get a value. So the first one, it should be 1, isn't it? This one is 0. It's always 1. Then this one is 0.9. First leg should be here. So the next leg, 0.9 power of 2, 0.81. Then you should get a value somewhere here. So the third one, 0.9 times 0.9 times 0.5, 0.7729. So this is the one. So keep on plotting this, you will see you're expecting to get a ACF which is gradually decay to converts to a constant or 0 at the end. Okay, so this is what the table has been indicated. If you use the ACF to identify the ARP models, you always see the tail off gradually. Okay, so this is what the meaning of tail off gradually. Okay, so it decays slowly to 0. Decays slowly to 0. Okay, guys, so this is for AR1 model. What about AR2 or higher order? So we will discuss that in the next session.